I'd like to start by talking through 5 different problems in related rates that are pretty different from each other. We're going to do 2 volume problems, 2 distance problems, and 1 angle problem. And actually, when I said do, we're not going to do them. We're not going to solve them completely. I'm going to talk through them so that you can see what the problems are kind of like, which hopefully will give you additional motivation to go ahead and start working on this. So now here's the first of my 5 sample problems that I'd like to talk through. These sample problems are all pulled directly from Newton, which is Creative Commons licensed attribution non-commercial. This is non-commercial use, and I am attributing it verbally right now. So here's a problem. An inverted cone is partially filled with water, as shown below, and they give us a picture. The radius of the inverted cone is 16 millimeters, and the height is 18 millimeters. So they're telling me about the shape of the container. And then it asks the question, if the volume of the water is increasing at a rate of 548 cubic millimeters per hour, fine, whatever, some volume. So the volume is increasing. That's what they're telling me. The volume is increasing. Look, this is the volume down here, and it's increasing. That means that dV dt has to be bigger than 0 because it's increasing. And in fact, they give me a positive number. So the volume is increasing. And if the volume is increasing of the water down in the bottom of the cone, that means that the height of the water also has to be increasing. Right? There's no way you can put water into the bottom of this cone and not have the height increase. It's impossible. The height has to increase if the volume increases, and if the height increases, then the volume increases. We should label that and call that H. We should probably label that and call that R so that we're labeling and naming the contents that we're really trying to study here. Okay, so the volume of the water is increasing at a rate of this thing right here. Okay. That's one rate. And then they're asking, what is the rate at which the height of the water is changing? And those two pieces are 2 rates of change that are going to be related to each other. dH dt equals question mark, because I don't know it. That's what we're being instructed to find. And dV dt is equal to 548. So we've got these 2 rates of change, and they're related to each other. And that's why these are called related rates problems. So there are these 2 rates of change and other related other variables as well, like the height of the water and the radius of the water and stuff like that. And they're all related to each other. And our mission is to discover that relationship, that mathematical relationship. So that's our responsibility, right? That's your responsibility when working through these problems. And it's going to come from, in this particular case, the fact that volume is equal to 1/3 of pi r squared h. So I have some static equation, but that's also true at any point in time. So it's also kind of a dynamic equation. And if I differentiate this with respect to time, I'm going to have dV dt popping up. I'm going to have dH dt popping up because v and h are both functions of time. This problem is emblematic of volume changing problems, related rates problems where we're studying how volume is changing. My goal isn't to work through the problem, it's to give you a flavor of what the problems look like so that we start seeing some common threads. Here's my second sample problem. I've got a cylindrical can that's partially filled with water. Okay, fine. So instead of an inverted cylinder, I've got a cylindrical can. It's partially filled with water. So there's a volume down here. And that has a height and a radius. And there's an overall shape to the container. That the radius of the overall container is 8 and the height of the overall container is 9. So that prescribes the overall shape of the container. And look at what we're being asked. If the volume of the water is decreasing at a rate of 527, what is the rate at which the height of the water is changing? So I'm given dV dt, and I need to find dH dt. These two rates of change are related. dH, dt, and dV, dt are related, right? If the volume here is changing, then the height has to also change. It's impossible for the volume to change without the height changing. And it's impossible for the height to change without the volume changing. So the two rates of change are related, and their ways that those rates of change are related is going to come from how the height and the volume are related. So this is going to come from the statement that volume is equal to pi r squared h. So we're going to come from, again, some statement that does not involve the rates of change, and from that we'll discover how the rates of change are related to each other. So we got a boat, and it's 186 miles east of some city. Fine. So here's a city, and I kind of like think of cities abstractly as like a bunch of skyscrapers, even though cities with a bunch of skyscrapers tend to be not my favorite cities. It doesn't matter. Smithville, and we're treating it as a point. So we're grossly reducing a city to a point. And then there's a boat, 186 miles due east. But that boat is traveling 27 miles per hour due south. So though the distance between the boat and Smithville is 186 miles initially, when the boat is some distance further south, the distance between the boat and the city has changed as well. So if I call the distance the boat has traveled x, and the distance between the boat and the city d, we can now ask the question, how fast is the distance between the boat and Smithville changing? That asks, what's dd dt? Right? They're asking us about the rate of change of some variable. And we're given it travels due south at a speed of 27 miles per hour, a rate of change for how fast the boat is traveling, that says that dx dt equals 27. So my related rates are dx dt and dd dt. Those two rates of change are related to each other. And our mission is to discover that relationship and then exploit it to figure out what is the value of ddt. And in this case, for this particular problem, it's going to come from the equation that looks static, but in fact is a time variant equation, that d of t squared equals x of t squared plus 186 squared. Right? There's this triangular relationship between those three variables, and it looks static, but actually d and x are both functions of time implicitly. I don't know what their form is, but that's not going to stop me from taking derivatives. So I have this equation which is true at all points in time, all moments in time, and then I can differentiate it to get an equation relating the rates of change of those quantities. And that's how this problem is really similar to the two volume problems that we talked about. There's some rates of change, and they're going to be related, and that relationship is going to come from something that looks like a static relationship, but is actually a relationship between the states of things. Question, wait, is d of t and x of t squared? And the answer is yes, because of the Pythagorean theorem, right? I've got a right triangle. And due to that right triangle, I've got that the square on the hypotenuse is equal to the sum of the squares on the two legs. And that's exactly this right here. So that's Pythagorean identity in some sense, Pythagorean equation. Oftentimes I find that coming up with this part, that is the hard part of the problem, because we don't give it to you. You got to come up with it. Let's talk through another distance type problem, and we'll see that this distance type problem is really similar to the previous one. Again, I'm putting off solutions for later. I'm talking through how are these problems similar to each other so you can see the pattern. I have a 165-inch rod leaning up against a wall. Ooh, and it's sliding down along the wall. And as it's doing that, it's falling away from the wall. This begs for a picture, does it not? I've got a wall, and I've got a floor, and then I've got a rod. I'm going to think of that as like, I don't know, a broom or something like that, because I've totally done this with a broom. I don't like thinking of it as a ladder because I have recurring dreams about falling on ladders, and this terrifies me. But this is 165, so that hypotenuse is always the same. And as the top of the broom or whatever it happens to be is sliding down the wall, the only way that it can remain at the same shape is if the bottom slides out. So if I call these distances h and x, it's clear that if h changes, x has to change, and if x changes, h has to change. Because it could be that the ladder is like close to all the way laying flat, or maybe it's like almost completely upright. There are all these different valid configurations of how the 165-inch rod is, and if the height of the point of leaning is changing, then the distance along the floor must also be changing. So our two related rates, in this case, are dh dt and dx dt. Let's pause for a second and investigate the problem statement. Which one is my unknown? Which one am I solving for? Let's see, a 165-inch rod is leaning up against a wall, and it's sliding. The vertical distance between the top of the rod and the floor is decreasing at a rate of 2 inches per second. So dh dt is known, and dx dt is unknown. What did you see about the language of this problem that tells you that it's dx dt that we're trying to figure out? All right, so it tells us that the vertical distance is 153. Oh, how fast? Okay. Ooh, there's that. There's the active work. That's what I'm hunting for. How fast? Right? What is the rate? The horizontal distance between the bottom of the rod and the base of the wall. Right? That's what I'm seeing. That's the thing that's asking, what is dx dt? The distance between the bottom of the rod and the base of the wall. Know also that it didn't call it dx dt. It described it. I made x up. I made it up. I made it up. I have creative license. I could have called that Q. I could have called that Z. I could have called that A. I can call it whatever the hell I want. And that's part of the challenge of these problems, is there's a lot of freedom in them. The further you go in calculus, the more freedom you'll find you have. What's the value of dh dt? I say it's known. What's the value of dh dt? How do we see that in the statement of this problem? It's in this part right here. Hunt for dh dt in that part of the problem statement. Yeah, dh dt is 2. How do I see that? I see that the vertical distance between the top of the rod and the floor is decreasing at 2 inches per second. Exactly, it's -2. It's -2. So I know not only that dh dt is known, but I know that dh dt is equal to -2. And dx dt is what I'm going to solve for eventually. So these rates are related to each other, and that relationship of those rates of change is going to come from the seemingly static relationship x squared plus h squared equals 165 squared. Right, so I don't start with something involving dh dt or dx dt. I start with something involving x and h. And then I'll get what the relationship between the rates of change is by doing implicit differentiation. A light is placed on the ground. Okay, there must be the ground. Here's the ground. And I have a light. There's a light. We're going to consider that as a point object, even though it has physical extent. So there's a light here. And they're saying that there's a distance between 31 feet to the point at which a javelin will be launched straight up into the air. Okay, so there's a launcher over here, and that this distance is 31 feet. We're going to launch a javelin into the air, which means that the javelin is going to go straight up, and the javelin lies somewhere on here. So if I consider my javelin is right there, I'm going to make up a name for the height of it. I'm going to call it h. All right, so that's kind of the first sentence tells me that. It says, determine the rate of change of the angle of elevation. The angle of elevation. Okay, so determine the rate of change of the angle of elevation. That's asking us to compute d theta dt. Right, that's my unknown. That's my unknown. D theta dt is unknown. We haven't really drawn the angle yet. I better come up with the angle of elevation from the light to the javelin. There's theta. Theta's that angle. And then they're going to say, okay, the height of the javelin is 28 feet. Fine. So that says h is 28. And the javelin is moving at a rate of 2 feet per second upwards. Ooh, 2 feet per second upwards. That says that dh dt is equal to positive 2. So my two rates of change are dh dt and d theta dt. And those two rates of change are related to each other because there's no way that the angle here can change unless the height is also changing. And if the height changes, then the angle of elevation also must change, right? Those rates of change are related to each other. And I don't start by writing down the relationship of the rates of change. I start by writing down the relationship at any point in time. And so the starting point for this one is going to be that tangent of theta is equal to h over 31, because I have tangent is opposite over adjacent. I've got my angle, opposite, adjacent. Opposite over adjacent is h over 31. So I've gone through this setup now, the basic setup for 5 different related rates problems. I haven't solved those problems, right? We haven't gone through the process of differentiating the seemingly static equations, just the state equations, but that's kind of the next step. So I'd like to talk through briefly my 5 steps to solving these problems, which are going to be different from other people's steps to solving these problems. I'm a distinct and unique human being, and so are all the other people who teach this kind of thing. So if you look at the book, or if you look at Steve Butler's resources, if you Google related rates problems and look at other people's solutions, or if you go check out Nancy Pye's solutions to these things online, we're going to talk about them slightly differently from each other. And I think that's a good thing. So maybe someone solves them in a way that makes more sense to you than the way I do it. As you can see, in all of these problems, starts with step 0 as a critical reading of the problem. And then step 1 is draw a picture. That's where I'm at. Maybe some people can solve these without pictures. I got nothing without drawing a picture. And I'm going to include both static things and things that are changing. I'm going to try to label my things that are changing with arrows to indicate, oh, this is going up, this is going down, what's happening with it. Because those arrows, those action arrows, help me identify when I differentiate later on in step 3, oh, I got to chain out a time derivative. Part of what makes this difficult is that you have to name things. It's not up to us as your instructors. It's up to you as the practitioner to name your things. Right? None of the 5 problems named every quantity. Some of them named some things, but most of them didn't name anything. And once I've named my things on my diagram, then I can start to edge toward a place where I can relate my variables in an equation that's true at all times. I'm not relating the rates of change. I'm relating the volume and the radius. I'm relating the distance over here and the distance over here. I'm relating the angles, but I'm not relating the rates of change. That comes from the next step. That's often the tricky part for many students. And once I have that equation, then I can use my differentiation skills from implicit differentiation to differentiate with respect to time. If something isn't changing, its derivative is 0, and it probably pulls out as a factor, multiplicative factor using the constant product rule, which is nice. But if something is changing, like a volume or a height or an angle or something like that, we're going to have to chain out the time derivative of it when we take ddt of both sides of the equation. And once I have that, then we're going to substitute every known quantity and try to identify the unknown, which in the fifth step we'll go ahead and solve for. Broadly speaking, these are the 5 steps that I use to approach these problems.